Hello friends, I welcome you all to this live session on structural analysis for seismic loads. I am delighted to share my experience with fellow architects and engineer friends. I am Hemant Vadalkar from Vadalkar and Associates. I am a consulting engineer and I would like to share some of my experience with you. The session will be for 45 minutes. If you want, you can send in your questions. We'll try to answer the questions at the end. Let me just tell you about the outline of my presentation. We'll be generally discussing about what are the earthquake effects and what are the loads required to be considered on the structures for design purpose. Then past earthquake experience and what is the damage that is happening due to these earthquakes and how we can avoid this type of damages, what kind of precautions are required to be taken. And finally, I will just share some of my projects with you, how the earthquake loads can be calculated, that we will try to discuss with you. So today's topic is structural analysis for seismic loads. Now generally, different type of loads are considered for structural design. Majority of the loads are like gravity loads, mostly the dead loads and live load. These are generally taken for design of the structure. But apart from that, there are other important loads like wind loads and earthquake or seismic loads. Those are also very, very important loads. Generally, they are lateral loads, while gravity loads are acting in a vertical direction. That is a major difference. Now, what are the effects of earthquake? See, earthquake never happens very, very frequently, but it is happening around the globe. No one knows when earthquake event can occur or where it can occur. So it is very difficult to predict the earthquake. But definitely wherever earthquake occurs, we have very, very disastrous effects on man-made structures, because earthquakes do not kill people, but our structures do, like our buildings. So the question is, can we learn some lessons from the past earthquake events? Are we retrospecting? And of course, our codes and standards are always getting updated based on the past experience, and that will be a continuous process, because we need to update our standards and the code practices based on the past experience what we have gathered. Now recently the code has been revised, that is the number is 1893 2016, criteria for earthquake resistant design of structures, which has been revised rather after 14 years, the long gap of 14 years. So of course, whatever experience is gained, that is to be implemented in our actual professional practice as well, and that's how the codes are also getting updated every time. Just if you have a look at the past history of earthquakes in our region, the major earthquake, if you can remember, that is Latur earthquake that was happened in 1993, and the magnitude was only 6.2, but you can see the number of deaths and the damages by this devastating earthquake. After that, the major earthquake was the Gujarat earthquake, which was in January 2001, and the magnitude was around 7.7. It was a bigger earthquake compared to the Latur earthquake, and thousands of people died in that earthquake, and of course there is a lot of loss of property also was very huge. Recently we have some other earthquakes in Nepal and in border area of Afghanistan, India and Pakistan also. So if you just see, after certain time, certain period, earthquakes are occurring around the globe. And why the earthquakes are happening? The reason is basically because there are plates which are moving towards each other with some rate. So the rate is, Asian plate is moving approximately at the rate of 47 millimeters per year. So that is the rate of movement of the plate. So when the stress at the fault zone exceeds the permissible limits, that triggers the earthquake, and very huge amount of energy is released. If you look at major earthquakes in the map, you can see different earthquakes here. The Latur is mentioned here, that happened in 1993, with this magnitude of 6.2. Then of course we have this 1991 also there was an earthquake in Uttarakhand, and we have the Gujarat earthquake, which is Bhuj area, and which is having the more magnitude of to 7.7. So this is the map which indicates at what time the earthquake occurred and what was the magnitude like. Now why earthquake is happening? What is the cause of the earthquake? So there are mainly two type of causes. One reason is a tectonic, it is called, other is a volcanic type of activity. The tectonic is associated with of course the faulting or other structural processes. As I said, all our continents, there are different plates and those are moving, and because of that the earthquake is happening. So this is the most common reason for triggering the earthquake. Sometimes with the volcanic activity also earthquake occurs, but relatively that percentage is small compared to the tectonic movement. So the majority of the earthquakes occur due to these tectonic movements. And there is a map of course available which is showing the fault zones, and in the I think Himalayan region these are very very active seismic zones are available. So these plates are moving, and sometimes they release very very large amount of energy. So that is a trigger point from which the shock waves emerge and we experience the earthquake, shaking of the ground that happens. Now what is the result of all this? Finally, because of the earthquake event, there is a large scale destruction of man-made structures. This is an example of this Nepal earthquake. You can see huge damage that is happening to the structures. Most of the time it was observed that the load bearing type of structures, or we can call it a masonry type of structures, which doesn't have much kind of ductility in that. These are called a very very brittle type of structures. So these structures fail quickly under this type of seismic activity because they don't have much lateral resistance or ability to absorb energy during these earthquake events. So that's why it is observed that maximum damage occurs in that type of structures which doesn't have that type of ductility or ability to absorb energy. This is of course an RCC type of structure, but still that has been damaged very very badly, and there must be some stilt here that has gone totally and the entire building has come down. Now just in a lighter vein I would like to just show you, this is the structure which is very very safe under wind as well as earthquake. This is a natural structure, it's a baya bird nest which just swings with wind or it will just shake with the earthquake, but nothing will happen. So we would like to have some type of simple structures which will be able to resist the earthquake. Now just coming to some of the terms related to earthquakes. So I will just show you some pictures about that as well. So there are some terms used all the time. One is called the focus or say hypocenter. Then there is epicenter. What is the epicenter? Is exactly the point on the surface vertically above the focus where the earthquake event occurs. That may be deep inside the ground. If you just project that point upward on the earth's surface, that is called epicenter. Then there are these two terms very very often used while describing the earthquake. One is the magnitude and another is the intensity of the earthquake. Now this magnitude is what exactly? Magnitude is nothing but a measure of its size at the source of the earthquake. So it is just related to the amount of energy that is being released during the event. That is the measure of this. And intensity is basically denotes the potential destructiveness of the earthquake at a given location. So this is a relative term. As you move away from the epicenter, you feel lesser and lesser impact of this. So that is nothing but the intensity. And there are some scales that are used to measure this. Richter scale is very popular for measuring the magnitude, and generally the intensity is measured in the Mercalli scale. So that is basically a perception of the damage. In terms of damage perceptions, some numbers are given and that's how it is measured. Now one thing I would like to just tell you, this earthquake is measured in Richter scale, it is on the log scale basically. And when I say earthquake of magnitude 5 and 6, so earthquake of magnitude 6 is 10 times more stronger than earthquake of magnitude 5. That is what the scale is. So it is log scale to the base 10. Now just to see how it is defined. So the focus point is where the earthquake actually occurs. It may be deep inside the ground where the energy, huge amount of energy released. And then if you just project that point above on the Earth's surface, that is called epicenter. And wherever you feel it, so the place of interest is maybe far away from this location. So there, how you feel about the earthquake, that is defined in terms of some intensity of earthquake. These are the basic terminologies used in this. So if you just look at this sketch on the left hand side, you have these isoseismal maps of the Bhuj earthquake. So earthquake is occurring somewhere here, and if you move away from the location of the epicenter, the intensity is being reduced. So it is denoted by some numbers, of course. That is called some scale. Now just to give an analogy, if you have some kind of say bulb, 100-watt bulb at certain location, and if you look at the brightness at some distance very close to this, you can see very, very bright image. But if you move away from that bulb, then the intensity keeps on reducing. So this is nothing but an intensity. If you can define in terms of intensity, this is nothing but your intensity of the earthquake. So as you move away from the epicenter, less and less effect you can just feel about this earthquake. Now what exactly is happening during the earthquake event? What is the effect? It is nothing but the inertial force that is being exerted on the structure. See, just to give an example in layman's language, if you are moving in a car or in a train, and if suddenly suppose driver applies the brake, then what happens? You just move forward. This is exactly what is happening during the earthquake. The ground starts shaking with some acceleration, and that's how some force is exerted on the structure. As per Newton's law, it is nothing but mass into the acceleration. That is kind of force that is being experienced by the structure during the event. Otherwise, the structure is subjected to only the gravity type of loads. It is just the vertical loads, we call it. But during the earthquake, in addition to that, the structure is subjected to some kind of horizontal force that is generated by the earthquake event. And if you don't design the structure for this type of accidental load or the force, then there is devastating damage. That is what is observed during all these previous earthquakes. Now I will just show you some of the pictures from the Gujarat earthquake, which is happened in 2001. So there was a lot of widespread damage during that type of earthquake as well, and the magnitude was around 7.7. Many buildings far away from that epicenter of Kutch area, like in Ahmedabad also, there was huge damage. And I was part of the survey team from Mumbai to survey the damaged buildings in that affected region. And we had some very, very interesting observations. Because of some bylaws in that there are large balconies, large projections were there, and of course there was open story, that was also a major cause of damage. And surprisingly, some places we noticed that there was no plinth beam provided, and that also made the building very, very vulnerable, because the foundation is maybe say about 10 feet down from the ground level, and if you avoid the tie beam, then the column height becomes almost 20 feet because you have the stilt parking there. And that's how the damage was there for some high-rise or multi-story building as well in Ahmedabad area. These are some of the photographs of the earthquake during the Bhuj earthquake 2001. And of course, there were some reports as well as some institutions they worked on is like say NICEE, and there are reports from EERI also, that is well-known institution in USA. So all these information and the reports are available for all the past earthquake. All the researchers are working on this. They have recorded the damages and trying to improve on the situation, and that's how our codes are getting revised after all these events. And not only the tall buildings, but even the ground floor structures also, or the small structures, load bearing structures, they also got damaged substantially during this type of earthquake. So there is sometimes some misnomer. Some people say that we are only building a very, very small structure like say ground plus 1 or ground plus 2 structure. Then why we should consider this type of effects? Because earthquake doesn't discriminate between what type of structures you are building. It is just creating horizontal force on the structure, and if the structure is not capable of carrying that kind of force or not able to absorb the energy during the earthquake event, then there is bound to be collapse for that type of structure. So one has to be very, very careful. You have to, of course, consider the design of the structure accordingly. These are some of the other photographs during the Bhuj earthquake. What you can see, the lift shafts are, some buildings are intact and other part of the building that collapsed, because the lift shaft was not either properly connected to the building or it was taken outside the building framing system. So that was one of the again reason. So the lift shaft as it is on its own is standing, but the building has collapsed. On the other picture, what you see again, the buildings on the stilt, the entire building block has come down and the stilt has vanished. So it is like a soft story effect. So that again our code is trying to address, how do you make our buildings safe against this type of catastrophe. Because what happens, the stiffness of the building on the first floor and above is substantially high compared to the stiffness at the lower floor level, at the ground floor level, which is called the stilt area, which is generally used for parking. So it is also called a weak story or open ground story. So that is again needs to be avoided, or you have to properly design the structure for this type of effects. Now we have learned some lessons, of course, from this 2001 Gujarat earthquake, and after mitigating this properly, then we can reduce the risk and the damages during the earthquake. This is just an illustration, a table which talks about what happened in 2001 earthquake, and after 2006 also there was an earthquake in Gujarat. So how many people were affected and what happened. So if you look at the comparison, this was in January 2001 and the next earthquake occurred on 6th April 2006. Both were in Gujarat. In the 2001 earthquake about 20,000 people died, but in 2006 earthquake there were no deaths reported. Injured number also very high in 2001 earthquake, but in 2006 around only 40 people were reported injured. And loss of life and property also is a very huge numbers during 2001 earthquake, but after that it was of course reduced. And then if you compare the magnitude also, the range of the earthquake, it was between 5.5 to 8, so it was around 7.7, that is at that Kutch area. And this earthquake also was having some less magnitude, but the effect of damage was much less, because we have learned some lessons, and of course some risk management techniques were adopted by people for designing the structures afterwards. So the knowledge is very, very important, and we have to of course apply the knowledge in practice to reduce the risk of the damage and casualties. So we have to of course learn, and then we have to improve all the time. So the question is asked whether really can we build earthquake resistant structures. So this is a very, very important question for us, and of course yes, we can do that. It is not that we do not have the knowledge. All the knowledge is available internationally as well as in India as well. We have good codes for this dealing with earthquake. But of course, then the question is, when something happens, then who is responsible? That is the question asked. And generally the blame game then starts, pinning the responsibility to one another. After even I remember in Gujarat earthquake also, I think some engineers were arrested at that time. But only engineering, whether only the engineer is only responsible, or there are some other factors which are responsible for the collapse basically. So that we have to understand in detail. So again, when I ask the question myself that who is responsible really for the failure of the structure, so I feel it is of course a joint responsibility of everyone, right from the owner, the approving authorities, the architects, the structural engineer, the contractors who are actually executing the project and building the structures, then the project management consultant who are actually monitoring the progress at site, and finally the occupants. See, all these are really responsible and they play a key role in the performance of the structure. We will see step by step how the performance of the structure is affected by these various factors. So in general, what are the factors? Those are responsible for affecting the performance of a structure. So first is the intensity and duration of the earthquake is a very, very vital factor, important factor, but we don't have control over this. What intensity and what is the duration of earthquake, so that we don't have any control on this. Then of course local site conditions and the geology of the given area. So here also we don't have any control on this, but this is also very, very important factor that is affecting the performance of the structure in the particular region. Then of course local soil strata is also very, very important, and the type of foundations. Yes, of course, type of foundation again is decided by the engineers. So we have some control on this type of foundations that we are going to choose. So again we have to be very judicious in selecting the correct type of foundations depending on the region and the soil strata available. And lastly, the materials used, the form of the structure, the size of the structure, and method of construction, and the materials used for the construction. This is of course definitely in our control. So we can control this last part basically, and then how do you control that risk of the damages, that let us see. Now when I say there are some more other factors, like say approving authority also is very important, because let me tell you, in Gujarat earthquake also what we observed, that there was some bylaw which was permitting the construction beyond the building line as a free of FSI, like say balcony or projections, that was not counted in FSI. So there was natural tendency to build more number of balconies or bigger projections, like we have seen up to 3-meter projections like balconies only. And now afterwards people have converted that balcony maybe into the room, or some people converted that balcony into toilets even, which is not really desirable. So again, that's why the approving authority or local building bylaws also is very important in controlling the type of damages, because lot of damage occurred because of the large projections and the cantilevers, and there were a lot of floating columns also that were used in those type of construction. So my point is, if you have the bylaws which allow you something and people are exploiting the loopholes in the bylaws to build more and more constructed area without counting in FSI, then that is what is going to happen. So I think that is a very important point we have to understand and remember. Then of course there is a size of the plot also matters, because based on the size of plot you have to just keep the open space requirements and the setbacks. Architect has to plan based on that. If the plot itself is very of odd shape or very narrow, then we have the limitation in planning of the building itself. So that is another factor which is of course finally affecting our performance. Then FSI permissible in the particular area, based on that it is decided whether you go taller or you spread the structure on the ground. Then there are some concessions available for getting the building permissions, approvals and all. And sometimes TDR is bought afterwards, and then the builder keeps on adding number of floors on the existing structure. So that also adds to the performance of the structure. Now I like this statement, a very noted structural engineer, Henry Degenkolb, what he says, if you have a very poor configuration to start with, all the engineer can do is to provide a band-aid just to improve basically poor solution as best as he can. But conversely, if you start with a very good configuration and a reasonable framing system, even a poor engineer cannot harm its ultimate performance too much. I think this is very important. We have to keep in mind that the performance of structure depends on this fact. Now what are the other factors? Let us just summarize this. One is the architectural planning. That accounts for the shape of the structure, the geometry in plan and elevation, that is most important. And symmetrical and simple structures are of course desirable. Code also says that. Then too elongated structure in plan or elevation is not recommended. Then your re-entrant angles are also undesirable in plan. And too many offsets also degrade the performance of the building. So these are some of the important parts, and these are some of the few features I am trying to show you. This is from very popular earthquake tips written by Professor C.V.R. Murthy. He is presently the director IIT Jodhpur. He has written a very nice book on this, so you must refer this book. Some of the pictures are from this publication only. If you have got too tall a structure is also not good, or you have the too long structure is also not good, or large in plan, that is generally to be avoided. That's what the recommendations are. So what we should have? We should have very simple type of plans like this, symmetrical structures. And if you have got very complex type of structures with curves and all, this is not desirable as far as seismic loads and earthquake is concerned. Then if you have called some kind of L type of shape of the building, then it is desirable to have some kind of expansion joints or separation joint it is called, just to separate the structures into simple shapes of the structures. That is desirable. So that is what again I am just making a list of this. In architectural planning, I will appeal to my all architect friends. If you can make a very simple geometry, then that helps of course in resisting the earthquake in a better way. So these concave structures, irregular shapes, sudden change in the mass or stiffness, either in plan or elevation is of course not desirable from earthquake point of view. Then if there are some large projections or there are some unbalanced mass in the building, that is also not desirable. Extra emphasis is given by some of the architects in maybe elevation treatment, because of course the building has to look good. So generally what is done is some type of boxing is provided, which generally adds some loose mass in the structure, which is of course is undesirable as far as the earthquake shaking is concerned, because what happens if the frame is also good but it lose mass or whatever is used for the elevation treatment, that will just fall down and people will get injured because of the falling debris. So as far as possible, this is to be avoided. That is what the earthquake code also suggests. So always it is better to have lighter mass, or the small mass is always better, because doctor also suggests or recommends all the time that okay, the patient, you should reduce your weight so that you should be healthy. Same thing happens for our buildings as well. If you have limited mass or less mass, it is always better. Similarly, low height to base ratio is also desirable. So this aspect ratio it is called. So it is generally advisable to be less than about 6, that is desirable. These are some of the other pictures of setbacks. You have a lot of setbacks in the building, suddenly the building is reducing, or you have some kind of system like this. When the podiums are there, you have this type of shapes. The tower is just going out, otherwise the base you have bigger dimensions. Or you have the weak story or the flexure story at the ground level. As I said, you have parking lots at the ground level, so the building becomes very weak at that location. So this is again creating problem during the earthquake events. Or if the building is planned on the slope like this, then also you have some kind of problem. Okay, or you have floating type of columns. So again the new code also says that this is not desirable to have floating columns in the system for resistance lateral loads. So this should be avoided as far as possible in the planning. And this has been proved again by all the past earthquakes, that if you have this type of short story effect in the structure, then there is a devastating damage, or there is a lot of damage that happens in the structure during the earthquake event. So we have to be very, very careful in planning and designing these type of structures. And if you have structure which is having unsymmetrical stiffness, that also creates the problem. The example is given as a swing. Suppose if you have a swing which has got different heights of the strings, then of course it is not going to swing properly, but it will twist. That is exactly happening in our building also. If you have got shear wall on only one side or two sides of the building, that creates a huge amount of torsion on the building, which is of course undesirable. So as far as the code is concerned, the code specifies 4 major attributes for a good structure. So what it says, robust structural configuration is of course desirable, and then you should have at least minimum elastic lateral stiffness for your structure. Similarly, you should have minimum lateral strength for the structure, and you should have adequate ductility. This is, I think, most important part, because what is ductility exactly? It is ability of a structure to absorb energy during the earthquake events. So this is what is desirable. And building with simple regular geometry and uniformly distributed mass and stiffness in plan or elevation is definitely desirable. So all our efforts should be made to eliminate irregularities by modifying maybe the architectural planning sometimes and structural configuration. So I appeal again to our engineer and architect friends that we have to, right from the beginning of the project, we have to coordinate with each other during the planning stage itself. Otherwise what happens, if architect is finalizing the plan and then giving it to structural engineer, then there is very less scope the structural engineer can do any modifications or do better structures in that. So right from the planning stage, if the engineer is involved, then we can of course generate better structures. Now as far as structural analysis is concerned and design is concerned, of course you need to have proper structural framing system and the members. You have to comply with all the latest code provisions, and proper frame shear wall structure interaction can be of course used in the planning. So it has been found that buildings containing the shear wall have performed better in the past earthquakes. So that is a suggestion by code also, that if you have shear wall system, it is much better. And of course, if you can keep uniform and continuous distribution of strength and stiffness in the building, that is of course desirable. So you should have sufficient member dimensions. If you look at the new code now, that is 13920, it stipulates some minimum column dimensions. Now that is minimum 300 is required. If you want to design a column, that you have to have minimum dimension of width of the column should be at least 300 millimeters. And again, another clause is also there that based on the diameter of bar you are putting in a beam, the column size should be about 20 times the diameter of bar that is in the beam. So these are again some requirements given in the latest codes. So detailing of the structural member is also very, very important. So detailed analysis as well as detailed drawing is required to get good structures. And you should have balanced lateral stiffness. So we need a stiffness in both the directions, because we never know how the earthquake is going to occur and in which direction it is going to come. So we have to have the balanced structural stiffness or resistance we call it, in both the direction, orthogonal directions. So design philosophy as per the earthquake resistance structure concern is basically you have to just look at strong column and weak beam concept. So the column should not fail. If the beam fails in flexure, that is desirable, that will form a plastic hinge over there, but the structure will not collapse. So this philosophy we must adopt now in our designs. This is another sketch which shows the poor practices which are generally being followed as on today even. We are just putting the bars of our beams inside the column, we are turning it inside and joggling the bars. But ideally, if you have got column width slightly more than the beam width, then we can take the bar straight. This is a good practice. If you try to do this, it is much better performing. What photograph you see here, if the beam bars are taken outside the column bars, then of course there is a failure in the cover zone itself and the beam will fail in shear as well. So this is not desirable. In many structures, when we surveyed the old buildings during our structural audit also, we noticed that there are links, those are missing in the beam column junctions. That is very, very important as far as the resistance is concerned. Because if you just put the links, then it will hold the joint together. Otherwise, during the very, very severe shaking, the joint, beam column joint can open up and there will maybe a collapse. So it is very important to place this confining links now as per the code provisions in the beam column junctions, and how it can be done, that is shown in this sketch. You have to put the beam bottom bar first, then you have to insert the links in the column in the junction part, and then you should put the top seal. That is the way you should do it at site. Otherwise, people will say at site is very difficult. Once you just place the beam cage in position, afterwards you can't place these links in the junction. So I think in the design also you have to show it in properly on the drawing, but only designing is not sufficient. The design must be implemented at site properly with all the due respect to the designer, and someone has to look after this implementation at site also. So strict supervision at site and the quality control by maybe the PMC or the site supervision staff is very, very essential. Otherwise, you are not able to construct a good structure. So total quality control on material and workmanship also is very, very important, along with of course the good design. And finally, I am coming to the occupants. What is the responsibility of the occupants? That is also very important. They should not carry out any unauthorized addition or alteration. That is generally observed that after building occupied, every flat owner feels that I am the owner of my flat, so I can do whatever I want. But that is not true, because it is part of the entire structural system. So sometimes people damage in the interior work also, sometimes the beam or the columns also, they just cut the core through that, which is really not desirable, not to be done. So damage to any structural member is disastrous. So make the structural changes during the interior, that is also happening, and that is the reason for many of the collapses that happened in Mumbai and elsewhere. The people have started removing the column in the building and the building came down. Then of course there are some enclosing the balconies and ducts also, that also happens because there is human greed to encroach on more and more area and overloading the structures by shifting the lafts or putting more water tanks inside and all these things. So that is of course detrimental to the structure. So we should not do this. Then you maintain the complete set of architecture and structure drawing with you and consult the proper structural engineer and architect before carrying out any alteration. That is, occupant should follow these guidelines. Otherwise, then you are damaging your own building. So always you involve structural engineer for guidance if you want to do any changes in your apartment or any building. And of course, the last part also very important. You have to carry out timely maintenance and repairs for your building. Otherwise, the buildings are neglected. Then building keep on deteriorating slowly along with time. And then one point it reaches that it is beyond repair. So it should not happen. If you want to keep a building healthy, functional, then you have to of course maintain the building with periodic inspection and technical audits. I am just now in the last part, I will just try to show you some of the small calculations, how the earthquake loads are calculated on the building. This is a very small example. I am just showing you. We have designed one building in IIT Bombay. So what code is given you all the formula. I am not going into the mathematical expressions and the formula, but in principle you have to just calculate the earthquake force, which is defined as VB, that is called a base shear. It is nothing but some coefficient AH into W. W is nothing but the seismic weight of the building. So how the factors are to be taken, that is explained in the code, but in principle it is some factor of your horizontal, the horizontal load is nothing but some fraction of the vertical load. W is your total seismic weight and this is some fraction of that. So you have to just calculate based on your total weight of the building, and based on the codal guideline you can just calculate the force. So in this example it is coming around 6% of the vertical force. So we can see here 0.06 is the value of your AH. So that I am multiplying with this total seismic weight W, and I am getting the earthquake force. That is the horizontal force I have to design my structure for. So there are two approaches given in the code. One is called equivalent static approach, wherein we convert the actual earthquake force as per the code provision into equivalent static force and apply the force. Really we are just using very fraction of the force. Actual force is very high. The real earthquake force is very high, but we are just taking a fraction of that, maybe 1/10 of the force we are considering for the design of the structure, but at least we should do that. That is what the intention of the code is. Now I will just show you some of the pictures of the structures which we have designed. This is just the framing plan of the building. You can just notice that there are cores, lift cores and the other central cores, which is giving the lateral resistance to the building, which is at the central portion of the structure, and there are wings. Initially the building was designed as a butterfly shaped building. So you can see these wings where you have the normal column frames and there are wings on this either side of the building. But slowly because of the more requirement of the area, again it has been closed and now it has become a box like structure again. This is the column layout, just to give an idea. Central portion what you see, this is the part of the core area which is resisting all the lateral force basically. These are the lift shafts and some more shear walls we have provided in the central portion, and this is the wing on either side of the building. This is what it is, and this is a lateral load that is being calculated as per the code provisions, and you have to apply the force in the orthogonal direction. It may be your x or z direction. So you have to apply that force along with your gravity loads like your dead loads and lie loads and design the structures accordingly. So you have to do the detailed calculations for this earthquake load as well. This is just an architectural impression. The building is right now under construction and shortly it will be completed, but this is how it looks like, the 3D view of the same structure. Some other building, one more building what we have designed in the past is for Institution of Chemical Technology. It is called ICT. This is the faculty building for their staff. This is steel plus 20-story structure, and I was fortunate to get good amount of shear walls in the building. So you can see the different shear walls over here. In both directions we have the walls, in vertical direction as well as in horizontal direction. We have sufficient number of walls to make the building stiff in both the directions. So that way it was a pretty good configuration designed by the architect. And again you have to just apply the force in the orthogonal direction, maybe in x direction and in z direction in the analysis part, and then design the structure for this. This is the completed view of the building, what you can see here, 20-story structure, and this is some close-up view of the building. This is a very good building with all the shear walls happening in the building inside. One more structure what we have designed, it is again a steel plus 16 floor structure done in Agasa near Thane it is, for Anantnag developers. So this building also has simple frames and we have designed this for all this earthquake resistance. Here we have taken one precaution as per the code provisions. We have provided additional shear walls in the stilt area to make it stiff in the stilt portion, because there was a parking for the stilt. So the building is having some soft story or weak ground floor. So to make it stiffer we have done this. Now again if you just notice it carefully, this is what you see the boxing part which the architects like to put in the elevation in the building. So this is all basically done in maybe some masonry work and then it is plastered to look like a solid box like this thing. But as I told you again, this type of boxing is really vulnerable during the earthquake event. Because of the loose mass it can just fall down. So we should try to avoid as far as possible, or sometimes the other option is then you can make it in RCC drop per like thing. So it is attached to the building firmly so that even during the shaking this mass will not come down from the building.